In this video, we're going to continue investigating the motion group of a solid cube. What I want to remind you of is that we already know certain information about the motion group. We know that the motion group can be embedded in S8 if we think about each rigid motion being a permutation of the vertices. But we also know that the motion group can be embedded in S6 if we think about each rigid motion being a permutation of the faces. And another thing that we know about the motion group is that we know that the motion group has order equal to 24. So it turns out that the motion group is a small subgroup of S8, and it's also a small subgroup of S6. And this brings up the question of, is there another way to think about this particular motion group? So is there another way to think about the motion group for the cube? And the thing that we want to kind of think about is there is one group of order 24 that we are very familiar with that is not commutative. We know that the motion group is not commutative because it's function composition. And so there is one group of order 24 that we know a lot about. And that would be S4, because the order of S4 is 24, which is 4 factorial. So the question is it possible that the motion group of a cube could be equal to S4? Well, the author of our textbook gives us the following cryptic theorem. It says that the group of rigid motions of a cube is indeed equal to S4. And I encourage you to stop the video and read this one paragraph proof. So stop the video. Now hopefully you stopped the video and you actually read this proof. It's a pretty dense proof. That's the thing that I want to notice. And so the things that I'm going to look at, and I kind of want to mark this proof up, is that there's a bunch of things that are pretty straightforward, and then there's some things that are not very straightforward. That there are 4 diagonals in a cube, that's not going to be too hard. Labeling them, that's not going to be too hard. And then from this point on, the proof really is very dense. And for many students at the level that you're at, this particular proof can very well give you the feeling of what the heck is going on. And then the accompanying thing is we have 2 figures. Well, this one is easy. This is just showing the labeling of the diagonals. And the interesting thing about this is that each diagonal, of course, is connecting 2 opposite points in the cube, but the author has chosen to label the points with the same number, which of course means that when we start tumbling this cube around, we're going to lose track of which 3 is where. And then there's this bizarre figure over here with this funny light, line in the middle. And what we notice immediately here is that the positions of the ones have swapped places with the positions of the twos. The threes and fours are basically in the same position. And the only thing is at this point we have really no good idea of exactly how the cube went from this particular version, which is the standard version, to this second version. So the question is, how? Actually, that's a bad color. The question is, how? What actually is the motion? And in particular, what is this funny looking light gray line supposed to be indicating? Well, we're going to look at each one of those things one step at a time. Well, the next part of the proof, the author starts talking about to obtain a transposition, we can rotate the cube 180 degrees about the axis joining the midpoints of opposite edges, and he cites the second figure in his proof. So he's citing the figure down here. And the midpoint of the opposite, the line joining the midpoint of the opposite edges is this light gray line. So this part here corresponds to that light line. And somehow rotating around this line gives us this picture. That's the author's claim. So the author's claim is if we rotate around that line, we get the second picture. Now, to understand this, it's easiest to see if we actually wind up making a new picture where the midpoints of both of the opposite sides are clearly indicated, and the line joining them is clearly indicated, and as a whole axis, which goes outside of the cube. So that's what this picture is. Well, what I want to do next is I actually want to study that picture in a lot more detail. Now, the author is talking about rotating 180 degrees around that line, and it doesn't matter which way we go, but this is what the kind of rotation that we want to be dealing with. And what we have to do is we have to figure out where each of these points goes in that particular rotation. Because if I know where all of those points go, then I'll know where the diagonals go. Well, to figure that out, what I want to notice is that we've got some important information that these points here that I'm putting in gray, they're all on one line, so they are collinear. And if I take a point not on a line and I look at the line and that point, that's going to make a plane. And that line continues down here, and this line continues down there, and here's another line. So this thing that I've kind of highlighted in gray appears to be in one plane, and it turns out that that is the case. And what I want to do next is I want to highlight it in colors that make it easier to see. So what I've done is I've highlighted the two edges that join those two endpoints, as well as the midpoint line. And now what we want to do is we actually want to draw that bow tie in its own plane. And so let's actually try and do that. We're going to have, well, let's see, we have the blue diagonal, and we have the brown diagonal, and we have the line of rotation, and of course we've got the two vertices at the top and the two vertices at the bottom. And so let's get that all labeled. So this is going to be 1 top, and this is going to be 1 bottom, and this will be 2 top, and this is 2 bottom. And of course, what we're doing is we are revolving around this line, and we're going 180 degrees, and because everything is supposed to be symmetric, 1 top is going to land on 2 top, and 2 top lands on 1 top, because those two lines are congruent, because this point here is the midpoint of 1 top and 2 top. And this point is the midpoint of 1 bottom and 2 bottom. And as a consequence, when we do the rotation, we also find out that 2 bottom goes to 1 bottom and 1 bottom goes back to 2 bottom. And what that actually means is that in the disjoint cycle decomposition, for this particular, I'm going to call alpha this rigid motion. So in the disjoint cycle decomposition for alpha, we're going to get part of alpha is going to be 1 top goes to 2 top, and 1 bottom goes to 2 bottom. So these two things are part of the disjoint cycles of alpha. Well, to find out what the rest of alpha's cycle decomposition is, we need to actually figure out what happens to the vertices 4 top and 4 bottom and 3 top and 3 bottom. And they're not in the plane that contains this bow tie. So they're clearly not in the plane that contains the bow tie. So to figure out what goes on, let's actually go to Mathematica and see if we can see anything there when we are starting to by revolving this thing around. Now, what I want to do in order to see this is I kind of want to try and get a good idea on what's really going on if I get the plane for 1 top and 2 top kind of in a horizontal position. But I also want to really look at the relationship between, there's the figure that I really want. I want to look at the relationship between the black axis with the arrows on it, the line that we're rotating around, and the red line right now. If we're just about on top of the green diagonal, it's easy to see that the red diagonal is perpendicular to, and if I spin this up to where I'm looking down the blue diagonal line, it's pretty easy to see that the green diagonal is also perpendicular to that black line of rotation. Now, what happens when you're looking at 2 points like 3 top and 3 bottom that are on a line perpendicular to the line of rotation? When we rotate 180 degrees, 3 top and 3 bottom switch places. And likewise, because, going back to the picture, because the red diagonal is perpendicular to the line of rotation, 4 top and 4 bottom are also just going to swap places under this particular rigid motion. Well, let's get that written down. And so what we want to do is we want to add to our situation that the red diagonal is perpendicular to the line of rotation, And that fact is going to say that 4 top is going to be sent to 4 bottom, and 4 bottom is sent to 4 top. So this particular transposition is also part of the disjoint cycle decomposition for our rigid transposition. But as we also saw, we also saw that our green diagonal is perpendicular to the line of rotation. And that's going to imply that 3 top and 3 bottom are in a 2 cycle. And that is also part of the disjoint cycle decomposition for alpha. And so what we now have is we actually do have, putting everything together, putting this stuff up here, this stuff up here together with what we've just talked about, we can see that alpha has disjoint cycle decomposition. 1 top goes to 2 top, 1 bottom goes to 2 bottom, and 4 top goes to 4 bottom, and 3 top goes to 3 bottom. Well, that's inside S8, where what we're looking at is S8 is acting on the vertices of the cube. But what I also want to notice is that what alpha is doing, and I want to come back and get another picture of the cube. So let's just get another picture. We're going to copy that picture. And we're going to clone that picture. And we're going to pull this down so that we can continue looking at this thing. What I want to notice is that because of what alpha is doing, since alpha is sending 1 top to 2 top and 1 bottom to 2 bottom, we can see that the blue diagonal is going to be sent to the round diagonal. Well, so what we want to say here is that if we're talking about alpha in terms of diagonals, alpha is going to send the blue diagonal to the brown diagonal. But since 4 top gets sent to 4 bottom and 4 bottom gets sent to 4 top, the red diagonal just gets sent to itself. Its endpoints just get swapped. And so it's important to realize that the red diagonal is its own special 1 cycle in the disjoint cycle decomposition for alpha as a permutation on the diagonals. And because alpha sends 3 top to 3 bottom, the green diagonal is also fixed. And so when we're looking at alpha inside of S4, it looks like blue goes to brown, brown goes to blue, red stays fixed, and green stays fixed. Now, all we have to do to get to the author's stuff is to realize that the author is called blue, the 1 diagonal, and the author is called the brown diagonal, the 2 diagonal, and the red diagonal is the 4 diagonal. And the green diagonal is the 3 diagonal, and that is inside S4, but those 1 cycles don't need to be written, and consequently, we see that alpha really is a transposition in S4, where S4 is acting on the diagonals. Let's get that written in stuff that somebody might be able to read. So it's acting on the diagonals of the cube. So we now understand the thing that the author was saying up here in this particular passage. We understand now how rotating about that line does indeed give us a transposition. Well, what comes next? The author claims that there are 6 such axes, and they all give transpositions. Well, we can easily count the axes if we start thinking about it, and I'm just going to kind of look at them. First of all, I'm going to notice that we've already got the first of these pairs of opposite lines where one of these axes would be. And then it's just a matter of saying, well, the second axis would connect those 2 opposite edges, and the third such axis would connect these 2 opposite edges, and the fourth such axis would connect these 2 opposite edges, and the fifth such axis would connect these 2 opposite edges, and the final axis would connect these 2 opposite edges. Now, they all are going to work in very much the same way that the one that we wound up analyzing in great detail, and so they all will wind up being transpositions. And it's important to know that you are going to you will investigate these other 5 axes of rotation in the next problem set. Well, the final part of the proof deals with the fact that somehow we can go from having all of the transpositions to that means all of S4 is part of the motion group of the cube. Well, I want to actually explicitly list all the transpositions inside S4. They're not very hard, and there are not very many of them. We start with 1. Well, 1 can go to 2, and 2 can go back to 1. Or 1 might go to 3, and 3 would go back to 1. Or 1 might go to 4, and 4 might go back, and 4 would go back to 1. Well, those are all of the transpositions involving 1. So then we look at the transpositions involving 2, but not 1. Well, 2 could go to 3, or 2 could go to 4. And then the remaining one is 3 goes to 4. These are all of them. So there are exactly 6 transpositions inside S4. And each one of these lives inside the motion group when we have that motion group acting on the diagonals. And since groups are closed, any product of the 6 transpositions has to lie inside the motion group. And then I finally want to remind you that we also know that every permutation inside of S4 can be written as a product of those transpositions. And what that means is that every permutation inside S4 is a rigid motion of the cube. And now remember that the two groups both have order 24, and so I simply want to make one more comment down here. Since the order of the motion group is exactly equal to 24, and that is the order of S4, that says we can conclude that we've got all of the permutations by looking, we've got all of the possible rigid symmetries by looking at the permutations in S4, and that says that the motion group is equal to S4 if we think of S4 as acting on the diagonals of the cube. More technically, it might be more accurate to say that the motion group is isomorphic to S4, and in this way we can then say that if we look at the motion, the set of permutations in S8 that correspond to rigid motions, that let's call that set H. That set H is a subgroup of S4, rather of S8, and that subgroup happens to be isomorphic to S4. The same thing can be said for the fact that we can think of the motion group as a subgroup of S6, where S6 is acting on the faces. And so if we happen to let, say, K be the set of permutations in S6 that correspond to rigid motions, so these are the rigid motions, of the cube, then we would say that K is a subgroup of S6 and K is isomorphic to S4.